Here we have a child pushing a sled, 0.4 kilogram sled. I'm not going to draw the child. I think that'll just confuse things. So the child pushes a sled, causing it to slide across the horizontal floor. We've got the accelerating force of 9 newtons, which is applied horizontally by the child. So this, just write 9 newtons in there. Ends abruptly as the sled passes the 0.1 meter mark. When the accelerating force stops, when the child, i.e. when the child releases the sled continues to slide, but slows down and comes to rest. So I've kind of I've drawn the starting conditions here. Here's the sled in the beginning, and there's the starting point. I'll just make it even with the front of the sled. So right here, from here to here, delta x equals 0.1 meters. That's how far the child pushes to the 0.1 meter mark. So child starts to push, and when the front edge is right here, then the child stops pushing, and then it keeps on going, moving across the floor. So in the beginning, while the child is pushing, we've got 4 forces acting on this sled. The force of the push, which is 9 newtons, pushing to the right. We've got the force of friction, which is going to the left. We've got the normal force, which is the ground pushing the sled up, and weight, or the force of gravity, pulling down. Normal force and weight are equal because this is not going up or down. It's at rest in the y dimension. So really the net force acting on it right now is going to have to do with this push and that friction, and we know the push is stronger, so the net force is going to be to the right. In a little while I'll deal with what's going to happen when the sled has been released and it's sliding across the floor coming to rest, but I'm going to leave that for now. So the first question, what's the sled's weight? Here's my solution to that. Weight equals mass times gravity. You just take the mass of the sled, multiply it by gravity, 3.92 newtons. What's the force of friction acting on the sled as it accelerates? We're given, and it says as it accelerates. We're not worried about the static friction when it's first beginning to move, just as it's accelerating. So coefficient of kinetic friction is 0.6. The force of friction is equal to mu times the normal force. And in this case, the normal force is equal to the weight. I already calculated the weight. I guess I could write that in here. This is 3.92 newtons. So then this is 3.92 newtons as well. So that's where this is coming from. There's mu. That's given in the problem. 3.92 newtons, that's the weight. So 2.35 newtons backward. I could call this negative 2.35 newtons, but I just decided to say it was backward. So the push is forward, the friction is backward. C, what's the net force acting on the sled while it's being pushed by the child? So the net force is, you could say it's ma, but it's also the sum of the forces. So these two, normal force and weight cancel out. So we just got the force of the push minus the force of friction. And when I was doing this before, I changed the problem around a little bit. It was rubber bands. So it says here band force. That's the force of the push, 9 newtons forward. Sorry, I got cut off. So the net force equals the push minus the friction. So 9 newtons minus 2.35, 6.65. That's the net force. The acceleration, now I can use net force equals ma, and I just have to plug in the mass of the sled and use the acceleration, use the force that I just calculated in C. So this is the net force. I should say net force, and that comes from the previous question, and that equals the mass of the sled times acceleration. So the acceleration is 6.65 divided by 0.4, or 16.6. E, what's the maximum velocity? So the maximum velocity is going to be reached when the front of the sled is right here. The child is pushing, so it starts out here, it gets pushed, 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 pushed. Here the pushing stops. Then it's going to slide, 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 and stop. So it's going to speed up until there, slow down until there. So I need to figure out the velocity at that point. And this is going to be a kinematics question, or a kinematics problem. So I have max velocity equals velocity at the end of the acceleration. I can use this formula where this is v0, that's equal to 0. And then right here I have v max, which is just going to be v. So v squared equals v0 squared, that's 0, plus 2a delta x. The acceleration I've already got. Acceleration is 16.6. Delta x is this distance over which it's pushed. That's 0.1. So multiply all these out, take their square root, and then you have the maximum velocity, 1.82 meters per second. F is asking for the force that's acting on the sled as it decelerates. So let me add in the sled as it's decelerating. So when it was being pushed, I had a push there. Now the push is gone. So I've still got the same forces as before. I've got the normal force, which is really irrelevant for this, except that it allows us to calculate friction. I've got the weight, and I've still got the force of friction. And the force of friction equals the normal force times mu, and the normal force equals the weight. None of these have changed. The weight's still the same because gravity and mass are still the same. So the normal force is the same, so the force of friction is the same. And the net force acting on this now, these two cancel. It's just friction. So the net force is only that. It's only negative 2.35 newtons. So there we go. That's the answer to F. Now I'm looking for the acceleration as it slows to a stop. Use net force equals ma. I know the net force. It's the force of friction. So negative 2.35 equals mass times acceleration. Plug in the mass of the sled. Solve for acceleration. It's going to be negative 2.35 divided by 0.4. This acceleration is negative, which means it's going to be slowing down. And finally, h. How far does it travel? I can use that same formula again. I know that the end velocity or the final velocity is 0. So here, this is now going to be v0, and this is going to be v. So this maximum velocity, it's going to start here at maximum velocity, and then slow down, slow down, slow down, and then stop. So that's the max velocity. This is 0. Oh, excuse me. Sorry. This is the final velocity, which is 0. This is the max velocity. The acceleration we just figured out. Delta x is what we're finding. So I plug everything in. Got 0 for the final velocity. 1.82 that's from a previous question. That was from part E. And then 2 times the acceleration I just found, delta x. So delta x has got to be 0.28. So the answer to how far it travels during deceleration is 0.28. Let's see, the last question or problem is multi-body problem, and we're supposed to find the accelerations of the objects and then the tensions in the two segments. So I did this last year. I just printed this out. I might explain it differently if I did it now. With these kinds of problems, the steps to follow are: first, take the whole thing and figure out the acceleration by writing net force as the sum of the forces, and then net force as ma, and set this equal to that, and then you can solve for the acceleration. So the first step would be to get a picture of all the forces. And I've got 7 kilograms, 4 kilograms, 8 kilograms. I have tension pulling this block up. I could also show this same tension pulling that block to the right. I've got tension pulling this block to the right. I could also put in the same tension pulling this block to the left, because the tension in a rope is the same at both ends, but its direction would be different. The direction is inward. So right here what I'm doing is getting the sum of all the forces. So this is, I guess I need to decide which way it's going to move. Actually, maybe I don't need to decide. Yeah, so this is kind of weird because friction opposes motion. So if you don't have any motion in the first place, you're not going to have any friction. So to decide which way the friction goes, you've got to decide which way things are being moved. And it's pretty obvious. This is hanging off the edge. Weight's going to pull this down. If these two objects can move, they're going to move to the right. Now, if the friction's strong enough, they won't move to the right. But we can figure out if it's strong enough. So the forces here on the whole thing, I don't need to include this tension or this tension because they cancel one another out. I don't need to include these tensions because they cancel out. Interior forces we don't need to include. The exterior forces, the forces that are coming from outside the system, are the weight of this. So gravity, which is an external thing, is pulling this down. And friction from this surface is pushing this block to the left because the block's being pulled to the right. Friction always opposes motion. This block's being pulled to the right, so friction is moving it to the left. So I've really just got 3 external forces. I've got the weight of this pulling down. I've got the friction of that going to the left and the friction of this going to the left. Up here I've calculated the 2 frictions for these blocks using mu, which is provided in the question. Mu is 0.2. So the mu equals mg. I've skipped a little step there. Force of friction equals mu times mg. Force of friction is really technically mu times the normal force, but on a level surface, the normal force is equal to gravity. So for this block, take mu, multiply it by mass, multiply it by g, and that gives me 7.84 newtons leftward because it's being pulled to the right. For this block, force of friction is going to be 7 kilograms times 0.2 times 9.8, and that all comes to 13.7 to the left. And then the weight of this is the mass times gravity, 8 times 9.8, and that gives me 78.4. So where I've written out my net force, 78.4, that's I'm calling it a rightward force since these blocks are being pulled to the right. And negative 13.7 is friction pulling on this. Negative 7.84 is friction pulling on that. So these two are leftward forces of friction. This is the rightward force of weight. And the net force is 56.8. So I have done this. I've gotten the sum of the forces. Now I'm just taking that value for the net force and I'm bringing it down here and I'm going to substitute it in here. And then I'm going to write net force a different way with MA. So the mass of this whole thing, since I'm considering the whole thing, is 7 plus 4 plus 8, which is 19. And if I multiply that by acceleration, then that gives me the net force. So here's net force equals MA, and this is net force equals sum of forces. I solve for A and I get 3 meters per second squared. That's the acceleration. Now for the tensions, you can't take the whole system because the tension this way and this way, T1 cancels out, and T2 goes this way, and those cancel out. So you can never really solve for anything because there's no T left. So to solve for tension, you have to pick out pieces of this and analyze a particular mass. So if it looks like I'm doing the 8 kilogram block first, so I just focus on this part of the picture. And I do the same thing I always do. The first is net force equals the sum of the forces. All the external forces acting on this block there's the rope pulling it up, and there's weight pulling it down. So I've written the net force equals T2, which is upward, minus the weight. And the weight I calculated using mg. 8 equals m, g is 9.8, multiply them, you get 78.4. The net force on this block is T2 minus 78.4. And now I'm going to set that equal to ma. M is the mass of just the block, because that's what we're considering now, times its acceleration, which is positive. Oh, no. Oh, no. Look what I did. So I wonder if let's see, could be this answer's right and I just realized what was going on. So this acceleration, I didn't really give a direction. That was foolhardy. This is moving down, this is moving to the right. So I made it positive, I guess, because I was talking right and left there. But now I'm talking up and down, and this acceleration should be downward, so this should be negative. So let's see what happens here. Negative 3 times 8 is 24. All right, so I did it right. I think I must have done my work somewhere else and then copied it and left out some stuff. So that should be negative 3. So when you solve for T2, this is the right answer. Add 78.4 to both sides and subtract 24 from it, and you get 54.4. And this is positive, so it's all good. It would be nice if I would say upward. Then for the 7 kilogram block, picking this one, you could do this with the middle block, but there are more forces on it, so I wouldn't bother. Always pick the ones on the end if you can. You just want to pick a block that's being affected by T1. So there are two forces acting on this. There's the tension pulling the block to the right, and there's friction pulling it to the left. So here's the sum of the forces. Tension minus friction. Rightward positive, leftward negative. And now I'm set it equal to the mass times the acceleration. Mass is 7, the acceleration is positive 3 because it's going to the right. So multiply that out, that's 21, then add this to both sides, you get 34.7.